Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Asymptotic River College in Sacramento, California. This is another lecture within the series of polynomial and rational functions for a pre-calculus class. And specifically, we're going to start talking about rational functions here. So you should have watched all the videos on polynomial functions containing, for example, information on dividing polynomials, end behavior of polynomials, zeros. Let's see, what else do we talk about? Maybe complex zeros, rational roots theorem, complete factorization theorem, all that fun stuff. So there's a lot of stuff that you probably have gone through so far. What we're going to do in this video is start our dive into rational functions by just talking about asymptotes of rational functions. And you have been exposed to this already in your prerequisite course, which would be either college algebra or college algebra with trigonometry. So there's not a lot that I need to actually introduce theoretically here, but we're still going to approach this so that we fill in those gaps. So here we go. Let's go ahead and state the domain of this rational function. By the way, I use the letter R for all my rational functions just to kind of make them different than polynomial functions. So let's state the domain of this rational function by building a table, or no, not by, but and build a table showing the function values as x gets close to any values that are not in the domain. So that's a pretty compound style question. So the main thing is state the domain of the function. And remember, with rational functions, the domains have restrictions, possibly, I'll say it that way because it's not always true, but possibly when their denominators are 0. So let's go ahead and find out when that denominator is 0. And we can see, just via factoring, that that denominator becomes 0 at 7 or -2. So let me zoom out. So that tells us that our domain of this rational function includes all real numbers not equal to -2 or 7. So I'll write that down here. And there you have it. It's just 3 groups of inequalities, essentially just saying you can take any number from -infinity all the way up to -2, but not including -2. So skip over that. Then start your next interval on the other side of -2 and going up to 7. Then skip over 7 and continue on to infinity. By the way, there's another way that you might see this listed, which is just like this. It just means that you allow x values in that interval or that union of intervals. Yet another way that some algebra students will list it, which is sort of okay in algebra, but as you move into calculus, it's not as good. But I'll list it like this, which essentially says the same thing. However, it's not as rigorous. It's often much better to get used to the interval notation, mainly because the number of things you're going to have to throw out from your domain gets larger and larger. So when that happens, you don't want to have a laundry list of things you throw out. Instead, it's just easier to write things as a union of intervals. All right, let's take a look at the rest of the problem here. So let's see, state the domain. Well, we're done with that. I'll go ahead and erase that. And build a table showing the function values as x gets close to any of those values not in the domain. And I'm going to use Desmos for this. So let's go ahead and take a look at that. So what I'm going to do here is just show you a little bit more of Desmos. Most people actually know how to use Desmos, but it's kind of nice to see some of the things you might not commonly use. So I built a rational function. I could turn it on or turn it off just by clicking the little open circle there. You can see that it does turn on to the right hand side or off. But I don't want to see it, actually. I'd rather build a table. And to build a table, you just click on add and you click on table there, and it builds a nice little table like this, but it doesn't do anything yet. And the way the tables are built in Desmos is that they have the subscript notation. So x sub 1 versus y sub 1. They assume that you're already using x for something else, so they don't want to use that. And they're assuming that you're using y for something else, so they don't want to use that either. However, you can replace the y value with your function name, evaluated x sub 1. And to get to the sub, that's shift and then the minus sign on your keyboard. That's how you get a subscript. And now, remember, we had domain issues at -2 and +7. So let's see what happens as x gets really close to -2. I'll go from the left-hand side or from below -2. So think of numbers less than -2. Those would be like -3. Notice it automatically fills in the y value. -2.5. So there you go. There's that. How about -2.1 or a -2.01? These numbers are getting close to -2, but what we would say is from the left-hand side. And you can actually see that the table is actually building, and let me turn off the grid because that's kind of annoying. But the table's actually plotting points as I am building the table here. So if I said, let's get a little closer to -2, I could say -2.0001. Oops, how about just 0.1? There we go. And how about -2.123 zeros and a 1? And you can see these outputs seem to be exploding, right? They're jumping off to what seems to be a super large number. And in fact, it's not that they're jumping to a super large number. It's just that they're going to a concept that's not a number. That concept is called infinity. And you can test the other side of -2. So think of the numbers that are to the right of -2 on the number line. So if you look to the right of the number line, like a -1. Or something to the closer to -2 would be -1.5, right? That's closer to -2. How about -1.9? That's really close to -2. Or -1.99. Or -1.999. -1.9999. You can see those numbers are also, and I'm going to do one more, even though it's off the screen. I'll just scroll the screen a little bit. You can see those numbers are actually approaching -infinity. Now, if I were to turn on the graph, let me go ahead and do this. You can see the asymptotic behavior as x gets really close to that -2, but from the left-hand side, the y values are rising to positive infinity, and that's what our table is showing. Same thing as x is approaching -2 from the right-hand side. I don't know if I said that correctly before. I think I said right-hand side by accident. But as x is approaching -2 from the left-hand side, the y values are jumping to positive infinity. As x is approaching -2 from the right-hand side, they're going to -infinity. And you can see that via the table right here. That's a great justification for using technology to help us understand behaviors, what's happening numerically as x gets really close to -2 or +7. Now, you do know, because you've graphed rational functions in your prerequisite courses, you know kind of, okay, well, x, or y goes to infinity or -infinity. I totally get that because they're vertical asymptotes there. But this conversation is going to help us out as we move forward in this lecture and future lectures. And here's the true definition of a vertical asymptote, since I just said it a moment ago. The function f is said to have a vertical asymptote, also known as a singularity, by the way, at the real number a, and by the way, it has to be a real number, okay? If it is true that f is approaching either positive or negative infinity. It's not that it approaches both positive or negative infinity. It's that f is approaching either positive infinity or f is approaching negative infinity. It doesn't have to approach both, though. And that should be true as either x is approaching a, and I want to note what this looks like. This notation is a calculus notation. This just means x is approaching a from below, is what we normally call it, but it really is, it means from the left. So as x approaches a from the left-hand side of a, you want your function to either approach plus or minus infinity. It doesn't actually have to be that, but whatever. And then the other notation says that x is approaching a from above or from the right, just as I've written there. So a lot of little notation that I'm trying to introduce from calculus, because you're in pre-calculus and you need to kind of get used to that notation as we get closer to the day that you set foot into a calculus course. There are three subtle points, though, that often get glossed over by both students and professors alike. First, the definition of a vertical asymptote only requires a function to have infinite behavior on one side of A for it to be called a vertical asymptote at A. That is, you could have a function, so maybe I should write this off to the side here, actually, because I have an example over there. So you could have a function, here's the x-axis, that has a vertical asymptote at some number. I'll just call this x equals -2 or something. Okay. So let's suppose you have a vertical asymptote at x equals -2. And your function, let's pretend, has the following behavior. F goes to, let's say, -infinity as x approaches a from the left. I'm sorry, it was supposed to be -2 from the left. So as x gets super close to -2 here, the function values drop down to -infinity. Once you have that behavior, let's just say it looks like that in the other direction. Once you have that behavior, you know, since dropping to it and a level of infinity, whether it's negative or positive, you know that this function must have a vertical asymptote at -2. However, there's no restriction on the other side for it to go to positive or negative infinity. So as an example, your function could do something like this and have a hole right there. That is not super common, I have to be very honest with you, but it still demonstrates the reality that all I need is one side of this vertical line for my function to have a behavior that's going to positive or negative infinity, so that I can call that vertical line the vertical asymptote. So all I need is one side of it where my function dips to negative infinity or rises to positive infinity, so I can call it a vertical asymptote. Kind of a lot to think about there, but that's one of the pieces that a lot of people don't realize or don't talk about. And I'll finish reading out this statement here. While most vertical asymptotes have infinite behavior on both sides, and that's very true, I would say 99% of them that you see in a math course have infinite behavior on both sides, there are a few rare cases where only a single-sided infinite behavior exists. In these cases, the function is still considered to have a vertical asymptote at x equals a. So this is the first subtlety. There's 3 of them, or 4 of them, I forget how many I listed, but let's go ahead and play with this first subtlety. For example, determine the domain of the function. Let's just start with that. Here's a function right here, and we're going to determine the domain of that function. Well, if you look at that function, 2 to a power in general, you can plug usually anything into a power. So 2 to the 78th or 2 to the negative 310th or something like that is usually okay. However, your power is actually a rational function. And that means that it has a denominator. And that means that denominator should never be 0. So I already see a domain issue. X should not ever be 0. So the true domain of this function f is all real numbers not equal to 0. So the domain of f, here's a good notation to see, d sub f means domain of f, is all x in the interval from negative infinity all the way up to 0, skipping over 0, and climbing beyond there. So there's the domain of our function. You can plug anything else in, just not 0, right? Because you could see that would cause division by 0. Then the second part of this says, hey, now go ahead and go to Desmos. It doesn't say that, but that's what we're going to do. And build a table showing the function values as x gets close to any value that's not in the domain of the function. Well, there's only one value that's not in the domain. So let's go ahead and hop over to Desmos and build a table for x getting really close to 0. Just as I did last time, I don't want to showcase what the graph looks like because that ruins the fun. So instead, what I'm going to do, I'll hit enter here and I'll hit add a table. Instead of the y values, I want f of x sub 1. So I'll put that in there. And now we want our x values to get really close to 0. Well, let's start on the right-hand side of 0. I usually do numbers, I start 1 unit away just to showcase the behavior, and then I get half that distance. And then I go to maybe 0.1, and then to 0.01. You can kind of see, like, okay, there's no need for me to go any further. If you know numbers, you know that this number right here, some 1.3 times 10 to the 30th, is essentially infinity to this computer. So we're done. We know that from the right-hand side, our function, as x approaches 0, tends to positive infinity. And here's the notation I'm going to use. It's not exactly calculus, but it's close. As x approaches 0 from the right-hand side, f of x, the y values, approach positive infinity. And just as a heads up, most of us will not write the positive in front of the infinity. Once you write infinity, it's assumed that it's positive. Unless you write a negative in front of it, then obviously it's negative infinity. So that one is done. We've gone from the right-hand side and we see the functions approaching infinity. Now let's try the other side of 0. So I'll plug in a -1, a negative 0.5, a negative 0.1, negative 0.01. And you see this, and if you're not 100% sure about numbers, there we go, you can see like 10 to the negative huge power. That's 1 over 10 to a huge power. 1 over 10 to a huge power is 1 over a huge number. 1 over a huge number is really close to 0. So these outputs, as x gets close to 0 from the left-hand side, and you can see it over on our graph here, they're getting close to a height of 0. Let me write that down. And that's the notation right there. As x approaches 0 from the left-hand side, our function values are getting really close to 0. Now this does not mean that the function exists at 0. It doesn't, actually. The function cannot exist at 0 because it would cause division by 0 if you were to plug 0 in for x. However, it does mean that we have an asymptote, a vertical asymptote at 0. And that is because at one side of x equals 0, our function's jumping off to infinity. Now, I just want to show you what this function looks like. Here it is. You can see the points we plotted, but you can see as x approaches 0 from the left-hand side, the function dives down and gets really close to a height of 0. Very close to a height of 0, in fact. But on the right-hand side, as x gets really close to 0, the y values fire up to infinity. They just keep climbing and climbing. And because of that infinite behavior on one side, that's known as a vertical asymptote that we have at x equals 0. So that was the first subtle point, that not all, just because you have a vertical asymptote for a function, it doesn't imply that both sides go to some level of infinity. Only one side needs to. The second subtle point was actually embedded in that last example. Vertical asymptotes are not restricted to rational functions. That's critical. You already know one function, not that last one, but you know of a function that has a vertical asymptote, y equals the natural log of x. So that function has a vertical asymptote at 0 just by the nature of the function itself. You can see that it dips to negative infinity as x approaches 0. So it has a vertical asymptote at x equals 0. So it's not true that you need a rational function to have a vertical asymptote. It could be a bunch of different kinds of functions. That's a very short subtlety, but still an important one. The third subtlety is that not all domain issues result in vertical asymptotes. And this one you run into in Algebra 2, but you often forget it as you move forward in mathematics because it becomes less of a frequent issue. In fact, it sort of disappears behind the scenes. But let's go ahead and go back to Desmos and build a table of values as x approaches 1 for this function. You should note, if you were to try to plug 1 into this function, you would get 0 over 0, and that is called indeterminate. So we cannot do that. 0 over 0 just is not a number. We don't know what that number is. So let's go ahead and see what happens when we go to Desmos. Again, I'm not going to show the graph of it yet because I just want to showcase the table, and we're going to allow x to approach 1. Let me go ahead and replace this with f of x sub 1. And let's change these values. So I want x to get close to 1. You don't have to start at 0 and then 0.5. You can just start at 0.9 and then 0.99, then 0.999, 0.9999. Hey, now if you take a look at those outputs, as x gets really close to 1, it looks like the y values are getting close to a half. Along the same lines, if you tried the other side of 1, so 1.1, this is the right-hand side of 1, or 1.01, or 1.001, let me scroll down a little bit, just for one last one, 1.0001. And you could see from the right-hand side, my dog just shook her head, you can see that from the right-hand side, the y values, again, look to be approaching 0.5, and in fact they are. I'm going to turn off that grid. I always hate the grid on Desmos. And you can see that as our x values are getting close to 1, I don't know if you can see that, but that is right there, x equals 1. As our x values are approaching that, the y values seem to be approaching a height of 0.5. So what's going on here? Why is it that we can't plug in 1 to the original function, right? Yet we don't have a vertical asymptote. I mean, if we tried to plug 1 in, we'd have division by 0. So what's going on here? Well, simply what's going on is that somebody has some algebra to do. And this is a mantra that I want you to think about throughout all of mathematics, that you do mathematics in the order that you've learned mathematics. So you do arithmetic before you do algebra. You do algebra before you do trigonometry. You do trigonometry before you do pre-calculus. And you do all of that stuff before you even touch calculus. And this idea of x getting really close to 1 is a calculus idea. So what you need to do first is some algebra. And the algebra you're going to do is factoring. That's a difference of squares in the denominator. And you're allowed to do factoring. And you can go ahead and say, oh, those pictures in both the numerator and the denominator cancel. So this statement is very, very similar. It's not exactly, I should say, but it's very similar to 1 over x plus 1. That's supposed to be a plus, but my pen went nutty. So it's just like 1 over x plus 1. And if you plug 1 into that, which you're not allowed to, but let's just pretend you did, you get 1 over 1 plus 1, or 1 over 2, or 0.5, which was exactly what the y values were approaching. This is a very, very important point to make, that these two are actually not equal. So x minus 1 over x squared minus 1 is not the same as 1 over x plus 1. Because technically, if you handed somebody this function right here, they would think they could plug in the number 1. But you, being the wizard behind the scenes, know that 1 cannot be plugged in. So x cannot be 1 here. And here, it looks as though x could be 1. And so these are not the same functions. The way you can make the distinction to somebody is you can say, hey, you know what I have? I have this function, and it's equal to 1 over x plus 1. But its domain is negative infinity to 1 union 1 to infinity. This ends up being a massive issue as you move forward in mathematics. You constantly have to remind people that, listen, the domain of this function is not what you think it is. It looks as though you could plug in one, but I promise you it was built from something that breaks when you plug one in. So please don't do that. It's kind of like that saying that, what is it? A team is only as strong as their weakest link or something like that. I forget exactly what the saying is, but you're only as strong as the weakest link. So the weakest link for this original function is x equals 1. You cannot plug that in. It has a domain issue there. And so this function you've been handed that was created from that has a weak link that's hidden from your vision. Sort of like if somebody built a house, from the outside, it's holding up a roof. It's 2 stories. It's got a lot of weight on it. Seems like it could hold a lot, but little do you know that they built it on a cracked foundation. And so if they don't tell you that, you'll assume that you can add a 3rd story or something like that. So just to let you know, you do have to mention to the world, if you built this function from other functions that have domain issues, you have to mention that to the world. And that is really the 3rd subtlety, that just because it looks like it looks like it should have a vertical asymptote, it's not necessarily true. Doesn't need to have a vertical asymptote if factors cancel, but you'll still have a domain issue there, but it won't be a vertical asymptote. A little convoluted, but there you have it. And on this page, I just basically summarized that. When simplifying expressions or functions, just keep track of domain issues that seem to disappear. In the end, state to the reader that those values are not in the domain. Very important. Now, the following how-to kind of gets rid of all the calculus concepts that we've been talking about and really just summarizes the algebra stuff. But if you're planning to move forward in calculus, I think it'd be really to your benefit to think about the calculus definition every once in a while. So, and like I've said in the previous videos, because you've learned this in a prerequisite course, I don't really mind showing you a recipe or a how-to. I would never do this if you were taking a calculus class, because in a calculus class, it's your first time being exposed to those concepts. There's no way I would say, okay, these are step 1, do this, step 2, do that. No. It's all about theory at that point. But to determine the vertical asymptotes given a rational function, you just get everything into a single term. So combine all your expressions into a single term. And then you note any domain issues before combining the terms. So that's a very, very important point to make, because when you combine terms, you might end up getting rid of domain issues, hiding them in the background or sweeping them under the rug. You need to, at least from the get-go, say, ooh, we've got these issues, these 3x values can't be plugged in. Then glue everything together. Factor denominators and numerators. So that's the second statement. And then if factors between numerators and denominators cancel, which they did in our last example, note the resulting domain issues. In other words, note that, hey, yes, I know what I'm handing you looks like you can plug one into, but turns out we canceled x minus 1 between numerator and denominator, which created a hidden little hole in our graph. So x can't be 1. Right? And then there's a vertical asymptote whenever the denominator of this simplified rational function is 0. And that's pretty much it. It sounds like a lot. It's actually not. You get so super used to this, you just run through it. Notice here that in our next group of examples, which you don't see them all, but there is a group of examples here. We're not worried anymore about x approaching a finite number like 3 or 7 or something like that. So we're sort of switching gears without doing an example is what I'm saying. But don't worry, we will do examples when we glue everything together at once. It's just that you've seen this stuff before, so don't feel the need to inundate this video with a ton of examples, even though you still get quite a few here. So we're going to adjust our original question, build a table of values showing what the function does as x goes to plus or minus infinity. And so in this case, again, I'll just jump over to Desmos. I want to tell you something here. You're not going to be using Desmos for everything. It's just really good to help visualize stuff initially. So there's the rational function. That was actually the rational function from our first example that we dealt with. And now we're going to build our table of values here. There's the table. Remember, replace y sub 1 with r of x sub 1. And this time we're going to allow x not to go to 7 or -2 or whatever it was. We're going to allow x to get super positive, going to positive infinity. So you can plug in numbers like 100 or 1,000 or 10,000. Now, obviously, these numbers are not infinite that x is approaching here, but they're large enough to be convincing. It looks as though as x goes to positive infinity, the y values are approaching 1. You could do the same thing in the negative direction. So -100, -1,000, -10,000, and you can go even larger if you want. But you see, the y values seem to be approaching 1 in both cases. And now I'm going to turn on the graph just to showcase this, and I'll zoom out. So you could see the y values as we go to negative infinity look to be going, as when I say we go to negative infinity, I mean the x values. As the x values go to negative infinity, it looks like there is some airspace here, and that distance is 1. Same thing if you go to positive infinity. Again, as I say you, I mean the x values. As x goes larger and larger, the y values seem to be tending towards a height of 1. You can see the y values in the points there. As I move it to the right, it just gets a little bit lower, a little bit lower. So it looks as though the statement would be, as x goes to either plus or minus infinity, the behavior is the same, whichever way it goes. The function is approaching a height of 1. And that's the way you want to think of it. So just notice here what this function looks like. Now we're going to take a second example. The second example is slightly different, in fact significantly different from the previous example. I want you to notice there is a difference between this example, specifically a single difference. There is only one difference. I changed that power, because if you look at the previous example, same numbers, everything else is the same, but the power on the numerator I decreased by 1. Let's go ahead and hop over to Desmos and see what happens as x goes to plus or minus infinity. And in this case, rather than going through and behind the scenes building it, I'm going to build it in front of your eyes. There you go, I've done it. So now notice, well, maybe I could change that function into s, but I'm not going to. Notice it is x minus 3 over x squared minus 5x minus 14, which was what was asked in the last example, or in this example. As x goes to large positive numbers, the y values go from 1/100th to 1/1000th to 1/10,000th. It looks like they're just going to 0. And again, if you plug in large negative numbers, -100, -1,000, -10,000, the y values seem to be getting close to a height of 0. Negative 9.99 times 10 to the negative fifth is negative 0.0000999. So it's a very small number, still negative, but very small. If you want to see it, zoom out, and you can see that the curve does, as x goes off to negative infinity, the curve does look like it is approaching a height of 0. I have to zoom in quite a bit, but you can see if I click and drag across, the heights, which are the y values, are very, very close to 0. Let me scroll over to the left a little bit further. Let's see if I can, there we go. So you can see 0.0095 in a few moments, 0.0094, right? So, and then 93. So it definitely is getting closer to 0. It's just taking its time to get there. And the same thing if you look on the positive infinite side. As x goes to positive infinity, the y values again seem to be going to 0. So I'll go ahead and write that in here. As x tends to positive or negative infinity, the behavior is the same on either side. our function values, s of x, they are approaching 0. This kind of reminds me, by the way, a lot of people when they learn this notation say, well, no, hold on. As x is approaching negative infinity, our function was approaching 0, but from below 0. That is true, but we don't, for the function values, we don't say that, we don't use that plus or minus superscript notation. So don't worry about that. Okay, we only use a superscript notation for x's, which we don't need for infinity. And that gets us to this next definition. So we had already defined the vertical asymptote. Now, here's the horizontal asymptote. A function f is said to have a horizontal asymptote at the line y equals k if either f of x approaches k. I shouldn't say if either. It should just say if. Let me get rid of that word either. If f of x approaches k as either x goes to negative infinity or x goes to positive infinity. Or it could be both, like we saw in the last two examples. I should mention here, just like we said with the vertical asymptote, all you really need is one side to go to a constant. So let's say that you have a function that looks like this. And as x is going to infinity, the y values seem to be approaching a height of, let's just say, 3. Well then, 3 is called a horizontal asymptote. On the other side, it could do this. Let's say that it does this. Let's actually say it just dives down forever over here. That could happen. That totally does happen, actually. So there's not a horizontal asymptote on the left-hand side, but on the right-hand side, there is a horizontal asymptote. So this is a horizontal asymptote. As x goes to infinity, the y values approach 3. Notice on the other side, there's no such horizontal asymptote, and that's okay. This function still has a horizontal asymptote. Asymptotes are basically very helpful for us to describe the behavior of a graph and a function. Horizontal asymptotes are used for long-term behavior. What does it look like as I zoom out, which you saw me doing in the Desmos app. And then vertical asymptotes are incredibly useful for telling a short-term behavior. What happens in the middle of the graph? What are our singularities? Where are our issues with this function? So let's take a look at one more example, and notice it's labeled part C, which means that it's just a continuation of the previous example. All I want to know is, what is the behavior as x goes to plus or minus infinity? In fact, I'll preset that language in here. Now notice something about this function. This function is exactly the same as the previous two, except for the exponent there. It's a 3 rather than a 2 or a 1. So let's go ahead and go back to Desmos and plug in a 3 for that exponent. So here we are back in Desmos. I'm just going to raise this to the power 3. Notice the table changes accordingly. That's why I'm using the same function name rather than the t of x here. And as x goes to positive infinity, or in other words, as x gets super duper large, you see the y values are getting really large as well. Essentially the same order. When I plug in 10,000, I get out roughly 10,000. When I plugged in 1,000, I got out roughly 1,000. So it looks as though as x gets very positive, the y values get very positive. As x goes to infinity, so does y. But look what happens on the other side. Plug in x equals negative 100, I get an output of negative 100. Negative 1,000, I get roughly a negative 1,000 as an output. Negative 10,000 as an input, I roughly get negative 10,000 as an output. So as x goes to negative infinity, it looks as though the y values are also going to negative infinity. And I'll go ahead and note that here. As x went to positive infinity, the table showcased that the y values approached positive infinity. As x went to negative infinity, again the table showcased the y values seem to be going to negative infinity. Now I didn't show the graph of that. I'll go ahead and do that, but before I do, I want you to note, if you take a look at the exponent here and the exponent downstairs, basically if you take a look at the degree of the numerator and the degree of the denominator, the degree of the numerator is 1 greater than the degree of the denominator. Had you done long division, you would have gotten a linear factor here. So I'm just going to say it's an x plus some number, plus a remainder over the divisor. In other words, as x gets super massive, it's going to look like this. And we'll showcase that in a little bit. You don't need to understand that 100% right now, but I'm just telling you that as in the long run, as x gets massive, it's going to mimic the behavior of this non-fractional term, or this non-fractional polynomial. So let's see that in Desmos. So I'm over here in Desmos. I'm just going to turn on the graph. And right now, it doesn't look like it's anything like crazy or awesome or anything. But then if I zoom out, and I keep zooming out, and I continue to zoom out, in the long run, it does look like a line, doesn't it? If you zoom out enough, the long run behavior takes over, and it looks like the line y equals x. Even though that's like a universe view, like you're looking from on a universal scale. You lose all the fine granular details when you're zoomed out that far. But if you zoom in to look at the humanity of it, you see there's some very special characteristics that you can't see from afar. In that view, that far zoomed out view, where you ignore the fine granularity details or fine granular details, that is known as the oblique asymptote. So a vertical asymptote is a vertical line. A horizontal asymptote is kind of the end behavior. If your function at the ends when you zoom out looks like a flat line, then you have a horizontal asymptote. But if your function doesn't look like a flat line as you zoom out, then you likely have an oblique asymptote, especially if it looks like that as you zoom out. It doesn't have to look like that though. It might look like this as you zoom out, or it might look like this as you zoom out. It just depends. But that is known as an oblique asymptote. Now, some people will call it a slant asymptote, but that only works, or that language is only useful if your asymptote is a line, which is why I don't use the word slant for the asymptote. I use oblique because the word oblique, covers all the cases. It's sort of like when a student says, oh, you know what you do when you multiply polynomials? You FOIL them out. That's not true. That's what you do when you multiply binomials. Polynomials, you do general distribution. And by the way, you could do that with binomials too. So you might as well just say, instead of using FOIL, you should say, when you multiply polynomials, you distribute. So that's the idea. That's why I use the word oblique. So here we're actually asked to find that oblique asymptote for our function. So let's go ahead and do that. I say using either long division or synthetic division. To be very honest with you, the conversation using synthetic division ends up being a bigger conversation. So for now, I'm just going to say using long division. Because again, it will work with synthetic division, don't get me wrong. But the problem is that it leads to a much bigger conversation, which I don't want to have in this lecture. That's more of an advanced move. So let's go ahead and for now, just use long division. I want to know how many times does x squared minus 5x minus 14 go into x cubed plus 0 x squared plus 0x minus 3. I need those placeholders in there. X squared. How many times does that go into x cubed? Well, we know that goes in x times. We could double check that work by multiplying this x against all three of these terms. That would be x times x squared, which is x cubed, x times a negative 5x, which is a negative 5x squared, and x times a negative 14, which is a negative 14x. Remember your arithmetic, you subtract that entire statement. In fact, I should have written that maybe in red to say you're subtracting that entire statement. I don't know why. X cubed minus x cubed, that's gone by design. 0x squared minus a negative 5x squared is a positive 5x squared. 0x minus a negative 14x is a positive 14x, and I'll bring down the negative 3 just because I want to. And I'll ask, how many times does that x squared, that's highlighted there, go into 5x squared? Well, that'd be 5 times. And actually, technically I could stop here, but I'm not going to because I want to showcase something. So 5 times each of these terms. Well, 5 times x squared is a 5x squared. 5 times a negative 5x is a negative 25x. And 5 times a negative 14 is a negative 70. Let me double check that math. 5, yep, negative 70. You're going to subtract that entire statement. 5x squared minus 5x squared is 0 by design. 14x plus 25x is 11x. And let's see, negative 3 plus 70 is a positive 67. And notice x squared does not divide nicely into that. So that is our remainder. I'll go ahead and circle that up. And I'll state that it's our remainder. Now, I did say you didn't have to actually go this far, but I want to showcase why. So that fraction, when you do division, the division algorithm says this will equal the quotient, which is x plus 5, plus the remainder, which is 11x plus 67, over the divisor. Divisor is that big old polynomial x squared minus 5x minus 14. Now, I'm going to draw your attention back to a previous example very quickly. This guy right here. Notice that the difference between this and the one that was above it was the power in the numerator. Turns out if the powers in the numerator are the same, and we'll write this down in a few moments, but if the powers in the numerator, or the degrees of the polynomials in the numerator and the denominator are the same, then your function will, at the edge points, or as x goes to plus or minus infinity, will tend to the ratio of their lead coefficients. The lead coefficient of the numerator here is 1. The lead coefficient of the denominator is 1. So as x goes to plus or minus infinity, the function will tend to the ratio of 1 over 1, which is 1. If, on the other hand, the degree of the numerator is less than the degree of the denominator, then the denominator approaches infinity much faster than the numerator. So you can think of this as the numerator, like if, let's say x is going to infinity, the numerator is like super huge, right? But the denominator has gone to that super huge number squared. It's much more massive. And in fact, if you do the division of huge divided by huge squared, that is going to be 1 over huge. Obviously, I'm simplifying everything there, but you get the idea. And 1 over something massive is essentially 0. So the rule of thumb here is if the numerator has less degree than the denominator, then as x goes to plus or minus infinity, that function, that rational function, will tend to 0. Now let me go back to our example at hand. And we're very interested in learning what happens as x goes to plus or minus infinity for this entire thing right here. Well, as x goes to plus or minus infinity, this fraction, because the numerator has less power than the denominator, that entire fraction will tend to 0. It'll disappear as time goes on. What will remain is this. This is what we would call the oblique asymptote. And again, some people will call it the slant asymptote. I just call it the oblique asymptote because that's a broader statement. So the behavior of our function in the long run will mimic x plus 5. So when you're handed a polynomial, or sorry, a rational function, where the numerator has more power, whoops, that's supposed to be a highlighter. When the numerator has more power than the denominator, you will have oblique asymptotes. You have to do long division to find those oblique asymptotes. And just to showcase it in Desmos here, let's go ahead and graph y equals x plus 5. Notice, in the long run, that is the behavior of our function, x plus 5. Let me turn it off so you can see. Turn it back on. Turn it off, on, off, on, off, on. Just do that all day long, right? But you know that as you zoom in, that behavior is not actually the true behavior of the function in the middle ground. It's only the behavior of the function in the long run. As you zoom in, the real function starts to appear. And you'll see there are some subtle differences between x plus 5 and our actual function. But over the long haul, they're essentially the same. And that gets us to our exact definition of oblique asymptotes, or slant asymptotes. So this is going to be a calculus style definition. You do not need to know the specific definition, but I'm just stating it because I like to be complete with what I'm talking about. Q of x, which in our last case was x plus 5, is called the oblique asymptote for the function f if, when you look at the difference between your function in that q of x, which again in our last function was, our last example is x plus 5, if that difference becomes 0 as x goes to either plus or minus infinity, or possibly both. Again, you're not going to use this. This is just the actual definition. You can kind of ignore this until you get to calculus. And in calculus, it'll be repeated again, so don't worry about it. But it is kind of, I just like the thoroughness of it to say, okay, well, this is the actual definition. If you look at the function that we were just working with, that x cubed, x cubed minus 3 over x squared minus 5x minus 14. If you were to look at that, which is actually just this, and you were to subtract off the oblique asymptote, so let me go ahead and just note, we have t of x, and we want to subtract off q of x, and we want that to approach 0. Well, t of x was x plus 5, actually, plus 11x plus 67 divided by x squared minus 5x minus 14. That was our original function after we did long division. If you subtract off what we think the slant or oblique asymptote is, well, do some little simple mathematics. X minus x cancels, 5 minus 5 cancels. This is going to be 11x plus 67 over x squared minus 5x minus 14, and that approaches 0 as x goes to plus or minus infinity. So because that remainder, that's kind of the way you want to think about it, because that remainder approaches 0 as x goes to plus or minus infinity, then you know by definition x plus 5 must be the oblique asymptote. Again, you do not need to know that definition for pre-calculus. I'm just writing it for rigor. And here is a summary of everything we've just kind of gone through. To determine the end behavior, whether it's a horizontal or oblique asymptote of a rational function, and the rational function I'm writing is r of x is equal to numerator of x over denominator of x. I've chosen those letters in that way, right? N stands for numerator, D stands for denominator, R stands for the original rational function. First thing you're going to do is combine all terms in the rational function into a single term. So basically glue everything together as a single fraction. Once you've done that, if the degree of the numerator is less than the degree of the denominator, then our rational function goes to 0. We have a horizontal asymptote at 0. Let me actually write that. I use HA for horizontal asymptote and VA for vertical asymptote and OA for oblique asymptote, by the way. So again, if the degree of the numerator is less than the degree of the denominator, then our rational function tends to 0 as x goes to plus or minus infinity. Or in other words, we have a horizontal asymptote at y equals 0. If the degree of the numerator and degree of the denominator are tied, they're both like third degree or something like that, then our rational function I should highlight the tie. Our rational function approaches some number, some non-zero number, as x goes to plus or minus infinity. That is, we have a horizontal asymptote at y equals k. But what is k? K is the ratio of the leading coefficients in the numerator and denominator. That's not bad. So if the numerator had a leading coefficient of 3 and the denominator had a leading coefficient of 8, then the function would approach 3/8 as x would go to plus or minus infinity. And finally, our last case, which we just saw, if the degree of the numerator is greater than the degree of the denominator, then our rational function mimics the behavior of some quotient. And that I chose Q carefully there because it stands for the word quotient. Our rational function will mimic that quotient as x goes to plus or minus infinity. And by the way, I use a capital Q later on, so I might as well use a capital Q here. There we go. Sorry about that. Where Q of x is the quotient when n is divided by d. That's it. So we will use this when we graph, and that will happen in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.